Hello Chem 1A, this is Chapter 4, Lecture Video 2, and we're going to be discussing chemical reactions or equations. Again, this time we're going to focus on balancing chemical equations. So when we write our products and our reactants in our chemical equation, like we learned in the last video, you have to include physical states, but you also need to do something known as balance the chemical equation. So chemical equations show relative amounts of the reactants and the products that are going to be formed in the case of products or used up in the case of the reactants. This is what makes the chemical equation better than simply writing a sentence that this reacts with this to form this. With a chemical equation, you can see numerically relative amounts of reactants and products being used up in the case of reactants and formed in the case of products. This is all based off of the law of the conservation of matter, which basically states that mass can neither be created nor destroyed, but it always has to be conserved. What this means is that when we have a chemical equation, we have to have the same number of each type of elements, atoms, on both sides of the reaction arrow. For instance, if I have one carbon on the left side, then at the end of the day, I must only have one carbon on the right side because I can't create a carbon atom from nothing. I can only move it around and change what it's attached to. The amount of matter in the system, in this case, in other words, does not change. It's conserved. So if we look at the decomposition of mercury 2 oxide, here is mercury 2 oxide, HgO, and we can see that this equation is already balanced. It has the 2's here. Well, let's look at what that would look like without those 2's. All right, so if we just kind of cover those up for now. Well, right now I have one mercury here and one mercury here. So there is one mercury on both sides of the reaction arrow. But I have two oxygens here and only one oxygen here. This is not acceptable because we know we can't just create another oxygen atom out of nothing. It needed to already be there. So I need to find a way to make sure that I have two oxygens on both sides. Now, how can I do that? I can multiply my mercury 2 oxide by 2 and have two of them decompose. And what this does is this 2 distributes in. Now I have two oxygens on the left side of my reaction arrow. I also have two oxygens on the right side because of this subscripted 2 here. This has effectively made sure that oxygen is balanced. However, by putting that 2 in front of the HgO, I didn't just make two oxygens on the left, I also made there be two mercuries on the left. So I need to continue to balance. Now, how can I do that? I can put a 2 in front of Hg, which will now give me two mercuries on both sides of the reaction arrow as well. So now if we count right, I have two mercuries over here and two mercuries over here, and I have two O's over here and two O's over here. This is what it means to have a balanced chemical equation, to have the same number of each element on both sides of the reaction arrow. Now there are some guidelines for how we can do this, and we'll get to them on the next slide. So when we want to balance a chemical equation, we got to do this according to the law of conservation of mass. This is not an optional thing. All chemical equations must be balanced. This means each element has to have the same number of atoms on both sides of the reaction arrow, products and reactants. Once the products and reactants are known, we cannot change them in order to balance the chemical equation. Now, this is a big deal here. A lot of students do this accidentally, and it's a common mistake to make. It usually means you either predicted the products of your reaction wrong, or you just tried to change the substance in order to make the reaction be balanced, and you can't do that. Coefficients are used to balance chemical equations. So for instance, if we look at this whole reaction, I can tell this is an unbalanced chemical equation. And I can tell that from this 2 here with sodium. This is telling me I have two sodium atoms on the product side. But on the reactant side, I only have one sodium atom. This means that the reaction is unbalanced. If any one element isn't balanced, then the whole thing isn't balanced. So one of the things I could do to balance this would be to put a 2 in front of NaHCO3. Now I have 2 sodiums here and 2 sodiums here, so sodium is balanced. Unfortunately, by putting this 2 here, I now have 2 hydrogens. So let's make sure there are 2 hydrogens on both sides. Hey, look, there are 2 hydrogens on both sides, so we're good there. This also means, however, I have 2 carbons on both sides. Currently, I only have this 1 carbon here, so I need to put a 2 in front of carbon. This also means that I now have 6 oxygens because 2 times 3 is 6. I need to make sure I have 6 oxygens on the product side. So here's 1. Here's 2 times 2, that's 4, that gives me 5 total, plus the last oxygen in H2O gives me 6 total oxygens. This reaction is now balanced by putting the 2 in front of the reactant and the 2 in front of CO2. This is required. We can't just leave a reaction be unbalanced. You always have to balance chemical reactions. There's never a time when we shouldn't have a balanced equation versus an unbalanced equation. So now, well, it was unbalanced and now it is balanced. So let's look at some steps that maybe guide us through this process. A lot of the steps to balancing chemical equations are much easier after you practice them a lot, much like naming. So when we write a chemical equation, the first thing to do is write out the formulas of the reactants and the products, and we have to include our physical states. So for instance, if I was given, in the last lecture video, I told you like ethane gas reacts with oxygen to form carbon dioxide gas and water vapor. Those were all in words. We need to translate those words, create formulas from that sentence, write the physical states next to them, and so on. That gets us through step 1. After that, we're going to look at our reaction and look for the compound that contains the most different elements, right? So, for instance, H2O has 3 atoms total. 2 plus 1 is 3, but it only actually has 2 different elements, right? Hydrogen and oxygen. So maybe that's the most complicated compound in your reaction. Maybe it's not. If there is more elements in a compound, that's the one we want to start looking at first. And we'll go through this in the next couple slides. We're going to balance elements that are by themselves at the very end. So for instance, if we have O2 gas in our reaction plus some other thing goes to some products, this is an element by itself, and we're going to wait till the very end of our reaction to balance an element that's by itself. At the very end, the nice thing about balancing problems is that you'll know whether you did it right. If you just check, add up all the elements on both sides of the arrow and check to make sure it's the same number, you're going to get the right answer if you just double check, or you'll know at least that you did it wrong if you just spend the 5 seconds it takes or 10 seconds it takes to check your work and see if you do in fact have equal numbers of each element on both sides of the reaction arrow. One of the things that you got to be careful with is we always need to have the simplest ratio or smallest coefficient values. For instance, if I have H2 plus O2 gas goes to H2O liquid, we'd first need to balance this. So I need a 2 here because that'll get me 2 oxygens on both sides, and then that gives me a 2 here. Now this is balanced correctly, but what if I somehow got that this goes to 4 H2O, 2 O2, and 4 H2 gas, right? If I somehow got this balanced equation, it would be wrong based on step 5. Why? Well, if you look at this, each one of these coefficients can be divided by 2 to give me 2 H2 gas reacts with 1 O2 gas and goes to 2 H2O gas. This is actually our correct answer. this would be incorrect because it's not fully simplified. All right, so let's do some example problems. So we have Al solid reacts with bromine to form aluminum bromide. Now, if we look at these, we're always going to go to this one first because it's the most complex compound in the reaction. These are both elements by themselves, and we want to balance them at the end. Now, one of the things I notice when I'm looking at this compound is there's 3 BRs here and only 2 there. This means I need to find a way to get these two to be the same number. Well, I know that if I multiply BR2 here by 3 and AlBr3 by 2, this gives me 3 times 2 is 6 BRs over here, and 2 times 3 over here gives me 6 BRs there. Now I can focus on Al. I know there are 2 Als here and only 1 there. So I'm going to need to put a 2 in front of Al on the reactant side. And this is an example of balancing our chemical equation. All right, let's do one more example, or a couple more examples. Here's a little bit of a harder one. So we have a lot of products. We have 3 products. We have 2 reactants in this case. And we need to find out which compound is the most complex. Now, there are actually 3 of them that kind of fit that description. This one has 2 elements in it. This one has 2 elements in it. This one has 2 elements in it. It actually doesn't matter a lot where you start here. You'll eventually get to the right number. For instance, I could start with H2O and go, oh, well, there's 2 hydrogens here and there are 3 hydrogens here. What's the lowest common value between 2 and 3? It's 6. Well, how can I get 3 or 6 hydrogens over here? I can multiply this guy by 3. 3 times 2 gives me 6 H's, right? Well, how can I get 6 H's over here? Well, I can put a 2 in front. 2 times 3 gives me 6 H's, all right? So now that I have those done, I can look somewhere else. I can maybe look at NH3. Well, we already know the hydrogens are good. Let's look at the nitrogens. We have 2 nitrogens here. We have 2 nitrogens here. There's 2 over here. There's 2 over here. Nitrogen is also balanced. Let's look at copper oxide now. So we have 1 copper here, and we have 1 copper here. So we're good there. Let's look at oxygen. I have 1 oxygen on this side, and I have 3 oxygens on this side. Uh-oh. How can I fix this? Well, I can put a 3 in front of this. But that changes my copper, right? Now I have 3 coppers and 3 oxygens. Well, the oxygens check out. Copper doesn't, though, because I have 3 here and only 1 here. I need to put a 3 in front of this copper to change this now to 3 coppers. And if we look at our numbers, we have 3 oxygens on both sides, we have 3 coppers on both sides, we have 6 hydrogens on both sides, and we have 2 nitrogens on both sides. This reaction is now fully balanced. All right, let's do one more example, and then we'll move on to one last slide. If we have iron reacting with oxygen to form this compound, iron 3 oxide, well, we know that this iron 3 oxide is the more complex one, so we're going to start here. Again, I'm going to start with oxygen, particularly because there's a 2 and a 3 involved. This means that my 2 substances need to have a common value, 3 and 2. That's going to be 6. So I'm going to put a 2 in front of Fe. Fe2O3, because that'll get 2 times 3 is 6 oxygens, and I'm going to put a 3 in front of the the oxygen. This will give me 6 oxygens on the left as well. Now by doing this, 2 times 2 here for iron gives me 4 irons total. I'm going to need to put a 4 in front of this iron to make sure it is in fact balanced. And there we have it. All right, so let's talk about one last little bit, combustion reactions. We learned about combustion reactions in chapter 3. right? A combustion reaction is where we have a fuel, most of the time an organic compound, reacting with oxygen gas. Now, the products of combustion reactions are always the same two substances, right? As long as we only have carbon, hydrogen, or maybe oxygen here, reacting with oxygen, we're always going to form CO2 and H2O. CO2 is going to be in the gaseous state. H2O is pretty much going to probably be in the gaseous state. This is an explosion, right? So most of the time, a lot of heat. The water that's being formed here isn't in the liquid state. This is propane, so I happen to know propane's a gas. I would expect you to know that oxygen is a gas at room temp. This guy, the propane, I would have probably given you its physical state on a test. I don't expect you to know every physical state out there. Just the most likely ones. For instance, I would expect you to know that if you're at room temperature, water is going to be a liquid, oxygen is going to be a gas, nitrogen is going to be a gas, hydrogen is going to be a gas. These are kind of things I would assume you would know. But substances like this guy, the propane or complex compounds, most of the time you'll either be given the physical state, or we'll talk about solubility rules later on in this chapter. Okay, so before we get to that second one, let's finish balancing, right? So next, we're going to balance this chemical reaction. Most of the time, we want to start with the compound that is reacting with oxygen. So I noticed there are 3 carbons here, and there's only 1 carbon over here. I'm going to put a 3 there. Next, I'm going to look at the hydrogen. I have 8 hydrogens here. I only have 2 over here. I'm going to put it 4 here because 4 times 2 is 8. Finally, I'm going to look at oxygen. I have 3 times 2 is 6 oxygens, plus 4 times 1 is another 4 oxygens, so a total of 10 oxygens on this side of the reaction. I'm going to put a 5 here to balance oxygen on the left. All right, so this is our balanced chemical equation. Let's do one more example. So here again, we have C3H8O now reacting with O2. This is again going to form CO2 and H2O, probably both in the gaseous state, definitely CO2 in the gaseous state. Again, I'm going to start with carbon. I know I have 3 carbons there. I'm going to put a 3 in front of CO2. That'll give me 3 carbons on both sides. Next, I'm going to put a 4 in front of H2O, again due to this 8 hydrogens. 4 times 2 gives me 8 hydrogens. Now, right now I have 10 oxygens on the left, or the right, sorry. And here's where it gets a little bit tricky. We have an oxygen in this compound. So I need 1 plus whatever O2's number is to add up to 10. But that would mean that I need whatever my blank here is times 2 to be 9. Or in other words, this number here would have to be 4.5, because 4.5 times 2 is 9, plus 1 is 10, and then it's balanced. But we can't have half of an O2 molecule in our balanced chemical equation. They have to be integer values, our coefficients. So in this scenario, what we need to do is, knowing that I would have to have put a 4.5 here, I need to multiply this whole thing by 2. This means that I have 2C3H8O, probably going to be a liquid, but again, I don't need you to know this guy's physical state. I would provide that. Plus 9O2 gas, because 2 times 4.5 is 9. This goes to 6 times CO2 gas, again, 2 times 3 is 6, plus 8 times H2O gas. And if we actually look at this, it's all balanced. 2 times 3, this gives me 6 carbons. 2 times 8 gives me 16 hydrogens. And I get 2 oxygens from this compound, plus another 18 oxygens here, so for a total of 20 oxygens in this compound, or on the reactant side. Now over here we have 6 carbons. We have 6 times 2 is 12 oxygens. Over here we have 8 times 2, that's 16 hydrogens. We have 8 times 1 is 8 oxygens. Well, 12 plus 8 gives me 20 oxygens. So everything's now balanced. All right, so let's do one last example here. NCHO plus oxygen, right? So we're going to get our same products here, carbon dioxide plus H2O, gas, and we need to balance it. So I have one carbon here, one carbon there. Great, that's balanced. I have two hydrogens here, I have two hydrogens there, also balanced. I have 1 plus 2, that's 3 oxygens on the left. I have 2 plus 1, that's 3 oxygens on the left. Actually, in this case, just simply writing the products of my reaction have it actually balanced. Everything's 1 to 1 to 1. Okay, so if you have any questions at all, please let me know. I'm always happy to help.